Hey everyone. So as Dan said, this will be part 3 of the series on talks on from Analytic to Algebraic. So I'll begin by reminding everyone where we got into in the last couple of talks and what it was that we were trying to achieve. So what we've been trying to do the whole time is find a way to take the Kullback-Leibler divergence, so the loss function for a statistical model, and bound it by a polynomial. And the reason we want to do this is that it would let us calculate a upper bound on the real log canonical threshold for that model. And so we're hoping to find a method to bound it by a polynomial of this form on the right. I'll call this equation 1. Where these aren't just any polynomials, but instead, if we take the model's regression function, f of x w, where w is the weight, and take the difference between that and the true function, which generates the true probability distribution, then if we can write that as some sort of series, where each term is a product of a polynomial in the weights and a function of the input. So that's where we're getting these polynomials from. And where we get the finite number of them, the capital J, is from the Hilbert basis theorem, which we discussed at the start. So the Hilbert basis theorem says that the ideal generated by all of those that whole sequence of polynomials is the same as the ideal generated by some finite number. Okay. So from there, a couple talks ago, we talked about Grobner bases and how once we've found a finite basis for this ideal, we are free to swap it with a Grobner basis for a chosen monomial order, and that won't change any of the properties like the RLCT. So we'll rewrite G as G0 up to GS as a Grobner basis for this ideal. And throughout the last couple talks, and for this talk, we'll be using graded lexicographic monomial order. Okay, so what we found fairly early on in the series of talks is that equation 1 will hold given some convergence conditions on the EJX things, and also the FJWs, which I'll skip those two conditions, but the sort of the hardest one to check, which we've been looking at in the most detail, is if the following series, so these polynomials are called the quotients. I'll remind everyone what they are in a second. But if these series are bounded for all W in W, so where each AJK is called a quotient, and they come from being able to write each polynomial in our sequence in terms of the Grobner basis. But importantly, we sort of talked about last week how these quotients aren't going to be unique. There could be lots of different things that could give an expression that looks the same, and that can make it hard to check this convergence. So in particular, one way you could get different quotients is by using the division algorithm to calculate them. And if you change the way these Grobner basis elements are ordered, that will change the quotients that are output. And that's because the division algorithm at each step makes a choice based on that order. So I'll go to the second board. But because of that issue, we investigated the generic division algorithm, which is similar to the standard one, but instead averages over all the divisors at each step. And using that generic division algorithm, we were able to find some fairly complicated looking expressions for the quotients. So I'll write that out and then try and remind everyone what all the notation in the following expression is. So the quotient of the kth element of the Grobner basis can be written as the sum over all multi-indices, such that k is in capital D alpha, so that's another way of saying that the leading term of gk divides w to the alpha, while lowercase d alpha is the size of that set, capital D alpha. Then we have the coefficient of w to the alpha in the polynomial fj, and then we have the monomial w to the alpha divided by the leading term of gk. And then we have a sum over all integers from 2 to infinity. And then for each m, we add up over all descending chains of multi-indices of length n, such that the leading term of gk divides the last element in that chain. Then we have all the, I guess, what are called average, you can call averaging factors for each of those indices in the chain. We take the coefficient of the first element in the chain, then we have a collection of real numbers associated to each adjacent pair of indices in the chain. And I'll remind everyone how these are defined in a second. And then the polynomial, or the monomial w to the beta m on the leading term of gk. So just to remind everyone, d alpha is the set that records which elements of the Grobner basis, which of those have leading terms which divide w to the alpha. And lowercase d alpha is just the size of that set. And then for the tau factors, we first defined, given a pair of multi-indices, alpha and beta, and then index from our Grobner basis, we define that as, we first look at the polynomial w to the alpha divided by the leading term of gk times all of gk, and we take the coefficient of w to the beta in that polynomial. And so this is only defined if k is in D alpha. In other words, if the leading term of gk divides w to the alpha, so that this fraction makes sense. And then when we write t alpha beta without any specific third index, that is adding up all over all the Grobner basis elements whose leading terms divide w to the alpha, and we add up those tau alpha beta k factors. So both of these things are real numbers. So there's obviously a lot of sort of, I mean, this is a fairly difficult expression to interpret. There's quite a bit going on there, but I'll go to the next board to talk about division graphs, which are a useful way to visualize what's going on in those expressions. And using the division graph, we can also write those expressions in a simpler looking way. Okay, so given a Grobner basis, which we'll again write as G0 up to GS. So the division graph is an oriented graph where the vertices are just all multi-indices in n variables. And we have an arrow from an index beta to another index alpha if that tau alpha beta factor is non-zero. I'll just mention that from the definition, tau alpha beta can only be non-zero if alpha is greater than or equal to beta in the chosen monomial order. And so that means in the division graph, you're only ever going to have arrows in non-decreasing directions. Okay, so in the expression for the quotient AJK, we had a sum over all chains, all descending chains of multi-indices of length m. And then I'll just write out the summed again. Okay, so if any of the tau beta I plus 1 factors are 0, then the whole term for that chain will be 0. So what that's saying is that the only non-zero terms in this expression they are ones which have a chain of indices or multi-indices which form a path in the division graph. So yeah, so for this product to be non-zero, each pair of adjacent indices have to be connected by an arrow in the division graph. So the only remaining terms in this sum are those which are associated to a path in that graph. So in other words, this sum can be thought of as being a sum over all paths of length m in the division graph. So we can just visualize like one of those terms as a bunch of indices in the division graph and arrows going along in one direction, and each arrow has a tau factor. Okay, so moving over to the last board. Given two indices, alpha and beta, where alpha is strictly greater than beta, we define k alpha beta as the sum over all paths of length 2 to infinity of where we add up over all descending chains of multi-indices where the first element in that chain is alpha and the last one is beta. And we include a bunch of the constants from the expression in for the AJKs. So in other words, this is a sum over all paths from beta to alpha in the division graph. And we also define k alpha alpha as 1 on lowercase d alpha if d alpha is non-zero, and 0 if d alpha is 0. Okay. So using, I will mention that, so the only thing that k alpha beta depends on is these, I guess, all these real numbers, which in turn only depend on the choice of Grobner basis. So they don't have anything to do with like the specific FJs. So you can think of all of this, like the division graph and these k alpha beta things being, it's coming from a Grobner basis and nothing else. But using this notation, we can rewrite the expression for the quotients, AJK, as the sum over all pairs of indices where the leading term of GK divides W to the beta, and then we just have we absorb all the complicated notation into k alpha beta. Then we have the coefficient of alpha in Fj and the monomial W to the beta on the leading term of Gk. So this looks a lot simpler. I will say that then all the work in doing a calculation is sort of hidden in this factor. And so I'll go back to the first board, and I think we've got all the definitions we need to actually prove a polynomial upper bound for a simple neural network. So this example comes from Watanabe's book, Algebraic Geometry and Singular Learning Theory. And so it's example 3.2 in his book. So in that example, he doesn't study it in order to get a polynomial upper bound. I think his focus is more on looking at the zero sets of the KL divergence. But we'll use the example to try and find an upper bound on the KL divergence. So the model is given by the regression function f of xw equals a sine bx plus c sine dx, where so the input is x and the weights are a, b, c, and d. So this can be thought of as a simple neural network with two neurons and sine activation functions, which I guess isn't very, it's not really a thing that people use in practice. But it's still useful to study this example because it turns out a lot of the polynomials that come out are the same for simple tanh networks. And so you can use this example to sort of do most of the work for a tanh, for studying a tanh network. And we also say that the true function which generates the true distribution is just 0 everywhere. So then we can look at the Taylor series for the model minus the true function. And so just using the Taylor series of sine, what that comes out to be is we just have the usual constants at the front with some factorials. And then each time we take a derivative, we just sign one of the c. And so we're doing the, sorry, I should have said that we're taking the Taylor series with respect to the input variable x and computing it about x is equals 0. And so then, each time we take a derivative with respect to x, a factor of b and d come out. So that comes out to be ab to the 2j plus 1 plus cd to the 2j plus 1 times x to the 2j plus 1. And so this is exactly the form that we need it to be in for, I guess, remark 7.6, which I guess started this whole series of talks, and is the form I guess we've been assuming the whole time, where each term is a product between a polynomial in the weights and a linearly independent function of the input. So where fj of w is 1 on the square root of 2j plus 1 factorial times ab to the 2j plus 1 plus cd to the 2j plus 1. And ej of x is minus 1 to the j square root of 2j plus 1 factorial x to the 2j plus 1. And so you might have noticed there seems to be some level of choice on how we split up this constant between the polynomials and the function of x. And so this choice actually turns out to be sort of important. In the first lecture, I think it was, we talked about how we need some convergence conditions on the series of EJs and the series of FJs, which I'm going to skip doing those calculations for this example. But I will say when we make this choice of to split up the constant this way, those work out. I guess the interesting thing is that if you sort of split it up differently, those convergence conditions might not hold. So it can take, I guess, yeah, just a bit of trial and error to see what works. But anyway, so we now have a sequence of polynomials, the FJs, and Watanabe, he shows that the first two generate the ideal of the whole sequence. So the ideal generated by all of those polynomials is equal to the ideal generated by f0 and f1. And the way he shows that is he finds a recursive statement writing fk plus 1 in terms of f0, f1, and fk minus 1. So sort of unraveling that recursive statement, you can see that only f0 and f1 matter. So I'll go to the second board. So what that tells us is that f0, which is also, I'm gonna drop the constants out the front for f0 and f1. It doesn't matter too much, just because we're just changing it for a finite number. But so I'll say f0 is ab plus cd, and f1 is ab3 plus cd3. So this is a basis for that ideal on the previous slide. Okay, and so all our methods using the generic division algorithm need us to be using a Grobner basis for graded lexicographic order. So we can calculate that using an algorithm called Buchberger's algorithm, or there's lots of computer algebra packages that can calculate Grobner bases automatically. So a Grobner basis for that ideal is G, which has 3 polynomials. The same one, the first one is actually the same as f0, so ab plus cd, while the second one is b squared cd minus cd3, and the third one is acd3 plus bc squared d squared. So we'll write these as G0, G1, and G2. And so all our calculations are going to need us to be using the leading terms of these basis elements. And so yeah, we're using graded lexicographic order, which I'll just remind everyone, it orders monomials first based on their total degree. And if two monomials have the same total degree, it compares them using basically alphabetical order. So the leading term of G0 is AB, the leading term of G1 is B squared CD, and the leading term of G2 is ACG3. Okay, so then following on from what we looked at before, we need to calculate the quotients using this basis. And so they were the expression we got to just a couple slides ago was that AJK is the sum over all pairs of indices where the leading term of GK divides W to the beta. Then we have this K alpha beta function, which was the sum over all paths from beta to alpha in the division graph. The coefficient of W to the alpha in Fj, and then the monomial W to the beta divided by the leading term of Gk. And so we need to calculate this for K equals 0, 1, and 2, because we have those three elements of our Grobner basis, and J equals 0 up to infinity, being the sequence of the Fj polynomials. So to calculate this, I guess the main thing we want to need to calculate is this K alpha beta thing. And that requires us to understand the division graph for that Grobner basis, or in other words, we want to calculate tau alpha beta for each pair of multi-indices. So let's go to the next board and start computing some of those. Okay, so let's first look at tau alpha beta 1. So that exists, I guess, yeah, by definition, that exists when the leading term of G1 divides W to the alpha. In other words, AB divides W to the alpha. As a multi-index, AB can be written as W to the 1, 1, 0, 0. So this is the same as saying alpha has to equal gamma plus 1, 1, 0, 0 for some multi-index gamma. Okay, so let's assume that AB divides W to the alpha. Then tau alpha beta 1 is W to the alpha on, I just realized I should be talking about G0 based on the way I've numbered the Grobner basis on the previous slide. Okay, so W to the alpha divided by the leading term of G0. Then we multiply that by all of G0 and take the coefficient of beta in that. So writing that out, that's W to the alpha plus W to the alpha on AB times CD, and we take the coefficient of beta. I should have said at the start, we are assuming alpha is greater than beta, so obviously this first term we can drop because it is not equal to W to the beta. So this is the coefficient of beta in the monomial W to the alpha on AB times CD. Writing everything in terms of multi-indices, that's w to the gamma plus 1, 1, 0, 0 on w to the 1, 1, 0, 0 times w to the 0, 0, 1, 1. And we take the coefficient of beta. That comes out as w to the gamma plus 0, 0, 1, 1. That's just a monomial. So the coefficient of w to the beta in that monomial is 1 if gamma plus 0, 0, 1, 1 equals beta, and 0 otherwise. So we can write this in terms of a Kronecker delta thing. Writing this as delta of beta equals gamma plus 0, 0, 1, 1. So this is just a way of writing the above equality. We can plug alpha back in place of gamma, so we can replace gamma with alpha minus 1, 1, 0, 0, and rearrange what's inside the delta, and that turns out to be delta of alpha equals beta plus 1, 1, minus 1, minus 1. Okay, and then going to the last board. So if we were to repeat the same sort of calculation, we get that tau alpha beta 2 is minus delta alpha equals 0 to 0 minus 2. Sorry, plus, let me erase some stuff there. So plus beta, and the one for the third, I just realized I messed up again the notation of the Grobner bases. That should be tau alpha beta 1 there, and tau alpha beta 2 is delta alpha equals beta plus 1 minus 1 minus 1, 1. And so tau alpha beta is the sum over all k's in D alpha tau alpha beta k. So we can write that as, so I'll write delta 0 alpha, which equals 1 if the leading term of G0 divides W to the alpha and is 0 otherwise, times the tau alpha beta 0, what we found for that. Then we have delta 1 alpha, which is 1 when the leading term of G1 divides W to the alpha and 0 otherwise. That's a 0. And then a similar thing for the final element of the Grobner basis. So, looking at this, if we take some multi-index beta, which we can look at this and think about, all right, which alphas could make this tau alpha beta thing non-zero, and there's only 3. So alpha could be beta plus 1, 1, minus 1, minus 1, or beta plus 0, 2, 0, minus 2, or beta plus 1, minus 1, minus 1, 1. So what that tells us is that any index beta can have 3 possible arrows out of it in the division graph. So in the division graph, if we have beta, there's at most 3 things that could have arrows from it, specifically beta plus 1, 1, minus 1, minus 1, beta plus 0, 2, 0, minus 2, and beta plus 1, minus 1, minus 1, 1. So, I mean, all 3 of these arrows don't have to exist, though, and that's because of these other deltas based on whether the leading term of G0 or G1 or G2 divide the endpoint of that arrow. Okay, so now we have those tau terms, we can try and actually do the calculation. I'm thinking I'm running a bit short on time. I was just wondering, Dan, is it okay if I go like 5 to 10 minutes over?
Yeah, no problem. I got a break after this. So.
Sure, thank you. Okay, so what we will calculate, we won't calculate all the quotients because they'll take quite a while. But what we will calculate is the quotients of the first element of the Grobner basis, G0. And so, just to remind everyone of the expression for that, it was the sum over all these k alpha beta things, the coefficients of fj, and these monomials. Okay, so the first thing we can do is we can look at fj, and that was 1 on square root of 2j plus 1 factorial ab to the 2j plus 1 plus cd to the 2j plus 1. So there's only 2 terms in fj. And so that means this fj alpha is only non-zero for those 2 specific monomials. So fj alpha is 1 on the square root of 2j plus 1 factorial if alpha is 1, 2j plus 1, 0, 0. So that's, in other words, alpha being ab to the 2j plus 1. Or if alpha is 0, 0, 1, 2j plus 1. And it's 0 otherwise. So there's only 2 of these alphas in the expression at the top that matter, so we can rewrite aj0 as sum where we first set alpha is 1, 2j plus 1, 0, 0. We add up over all smaller indices beta. And so this 0 in being in d beta thing, we can write that as such that ab divides w to the beta. I'm just writing out the expression. Then just from above, the coefficient from f is this factorial. Then we have w to the beta on ab, which is the leading term of g0. I'll call this sum term 1. And the second one is where we set alpha as 0, 0, 1, 2j plus 1. So alpha is cd to the 2j plus 1 term. And then everything that appears in that sum is pretty much the same thing. Oops. Although this should be 0, 0, 1, 2j plus 1. I'll call this one part 2. I will only calculate part 1 though, and the computation of expression 2 is pretty similar. So going to the second board, okay, so we're computing 1. So let's just set alpha equals 1, 2j plus 1, 0, 0. Okay, so what the process is going to be is we're going to use the expression for tau alpha beta to work out first, okay, which indices beta that are smaller than alpha can have paths to alpha in the division graph. And then we're going to look at that in a bit more detail and realize that we can actually rule out most of those potential paths. And then from there, it will be quite simple to compute the quotient aj0. Okay, so first we have that k alpha alpha is 1 on lowercase d alpha, so that's the number of leading terms in the Grobner basis which divide w to the alpha. So in this case, w to the alpha is ab to the 2j plus 1, while our leading terms were ab, I think b squared cd, and ac d3, and the only one that divides w to the alpha is ab, and so that equals 1. Meanwhile, the only indices beta which appear in the expression for 1, they are those which are divisible by AB. So, in other words, that can only happen if beta can be written as gamma plus 1, 1, 0, 0 for some multi-index gamma. Meanwhile, if we look at the expression for tau alpha beta, which is on the final board, I'll just say alpha prime. So this alpha prime is different from the alpha we set fixed above there. But the expression for a general tau alpha prime beta, that tells us there can be a path in the division graph from beta to alpha only if alpha and beta lie on the same lattice spanned by the three vectors, which are at v0, which is 1, 1, minus 1, minus 1, v1, which is O2, O minus 2, and V3, which is 1, minus 1, minus 1, 1. So in other words, for any path from beta to alpha to possibly exist, we need to be able to write alpha equals beta plus n1 times v0. Sorry, n0, I should say times v0 plus n1 times v1 plus n2 times v2. For some non-negative integers n0, n1, and n2. And so alpha was 1, 2j plus 1, 0, 0. We had the condition that beta has to equal gamma plus 1, 1, 0, 0. So we can plug that in for beta here and rearrange to solve for gamma. And what that gives is that gamma would have to equal 0, 2j, 2j 0, 0 plus n1 times minus 1. So we're moving everything over to the other side, so just swap the signs. Oh, sorry, n0, n2, n1, sorry, O minus 2, O2 plus n2 minus 1, 1, 1, minus 1. And so gamma had to be a multi-index, so all of its components had to be non-negative. That can only happen if n0 is 0 and n2 is 0. Otherwise, if either of those are non-zero, the first component of gamma would be negative. Meanwhile, n1 can be anywhere from 0 up to j. Okay, so what that tells us is that beta, which the indices beta, which may have paths to alpha, we can write them, we can index them by beta n1. They are alpha, which was 1, 2j plus 1, 0, 0, plus n1, O minus 2, O 2, where n1 can be 0 up to j. But since we were assuming beta is strictly less than alpha, we can cut out the n1 equals 0 case. Okay, and so from beta n1 to get to alpha, the only potential path that could exist would be going n1 steps along the vector v1. Okay, so what we found is which indices could have paths to alpha and what those paths could be. But the tau term for beta going to beta plus v2, that, if we go back to our definition of what tau was, is just this delta 1, v1 instead of v2 there, beta plus v1. So what that is minus 1 if the leading term of g1, which was b squared cd, if that divides the endpoint of that step, so beta plus v1, and 0 otherwise. So for one of these steps in the above sketch to actually be an arrow in the division graph, we need b squared cd to divide the endpoint. But everything, all the indices in this path have their third component 0. So beta n1 starts at like starts with third component 0, and v1 going along the vector v1 doesn't change the third component. While b squared cd is divisible by c, which in other words its third component is 1, and so b squared cd doesn't divide beta n1 plus let's say k b1 for any k. So what we can say is this path doesn't exist. So what we found is that given our choice of alpha, which was 1, 2j plus 1, 0, 0, there aren't actually any smaller indices beta with paths to alpha in the division graph. So what that tells us is that only the k alpha term contributes to expression 1. And so what that comes out as is that expression 1 is k alpha times the coefficient of alpha in fj, which was this factorial, times w to the alpha, which is ab to the 2j plus 1 on the leading term of g0, which is ab. And then moving to the final board, we saw that k alpha was 1, so that means part 1 of the expression for the quotient is b to the 2j on square root of 2j plus 1 factorial. Okay, so then you can do a similar calculation for part 2 of the expression. And what you get from that is that that whole second sum is actually 0. So from that we get that the quotient aj0 is just b to the 2j plus, sorry, b to the 2j on the square root of 2j plus 1 factorial. We can go and check the convergence. So we add up all those quotients we've just found, we first square them. And what that is the sum from 0 to infinity of b to the 4j on 2j plus 1 factorial. And so you can use the ratio test to show that this converges for all values of b. I think you can use, you can use something like the Weierstrass M test to show that this is bounded on all compact weight spaces. And if you do the same type of calculation or similar calculations, you get the same result for this series involving the quotients for the for G1 and G2, the other elements of the Grobner basis. So you get this same result, that the sum of all their squares is bounded on any compact weight space. So I'll quickly run back to the first board to conclude the talk. Okay, so from all that, we've shown everything that we need for the upper bound to hold. So we can conclude for this model, which is the 2-neuron network with sign activations, there's some positive constant C1, so that the KL divergence is smaller than we just square each of the Grobner basis elements. But we saw that once we have a finite basis, we're free to swap it without changing the Lipschitz equivalence. So we can go back to our original basis of the ideal. So there's some other constant which gives us a bound where our polynomials are just these AB plus CD and AB3 plus CD3, which sort of it's more clear how that relates to the structure of the network, I think. Okay, so that's how these generic division algorithm methods can be used to prove an upper bound of the KL divergence. So what we can say is that it works in this example. Unfortunately, I guess even in this simple example, the calculation is quite long and intricate, and there's lots of notation to define. And so when we've tried applying this to more complicated models, so for example, 3 neurons, the calculation, at least for me, became too difficult to do by hand. So at the moment, where it still seems like we're sort of far away, we're pretty far from getting a general method for proving these upper bounds, but it is still, I think, sort of interesting that this generic division algorithm works out for this example. All right, so that wraps up my series of talks. Yeah, thanks for listening. If you have any questions, I'll stick around for a minute.
Yeah, thanks a lot. That was great.
Thank you.